Okay, scholars, let's have another look at the definite integral. We've already looked at the integral once before. The idea of the definite integral, remember, is it found the area underneath a curve. So if I had some function f and I was looking from a to b, if I integrated f dx from a to b, it found the area underneath the curve. Um, the application piece, which we used quite a bit, let's say we were integrating a velocity function from 1 to 3. We remembered that velocity was just the derivative of my position curve. And the fundamental theorem of calculus said that this equals s of 3 minus s of 1, which was my displacement. I don't want to make that look like a dividing sign, so let's do this. Hopefully these ideas are uh, triggering some memories. That's the whole point. But what we're going to embark on right now, what we hope to accomplish by the end of this video, is given the definite integral, we want to be able to solve all of these by hand. So to solve without the calculator. That is the goal. So just as a reminder, the idea of the integral, this is all important for us to keep these big topics close to heart. The idea of the definite integral is that we took a bunch of little rectangles, and each of those rectangles had width delta x. And this idea of adding up rectangles has a special name, and it's called the Riemann sums method. And if we add up all of these, if we add up all these rectangles, what we get is an approximation of the area underneath the curve. And the the key idea that a key development in calculus was for us to take lots and lots of rectangles. In other words, let's let the number of rectangles approach infinity. And when the number of rectangles actually approach infinity, our estimation of the area becomes exact, and the Riemann sums equals the definite integral. So these are just some key theory ideas that, as we relook at definite integrals, we want to keep in mind. Okay, another major important idea, the fundamental theorem of calculus. And the fundamental theorem of calculus says that if we're integrating a function where the function we often say is like the derivative, and I like to they use lowercase to represent derivative. I think it's clearer just to say, if we're taking the integral of some derivative, the way that we evaluate that is we evaluate the antiderivative at the given limits and find the difference of them. So, what the big sort of key piece that we're going to be doing today is taking some function, and what we're going to need to be able to do is take the antiderivative, not take the or not take it, find the antiderivative. Because as long as we can find the antiderivative, as long as we can find that function f of x, then it's very simple to evaluate a definite integral. Well, let's look at an example where the antiderivative is already given to us. Um, so we are trying to, we're not going to do this Riemann sums. We're trying to evaluate this definite integral right here, and we notice that the function, ln x, is the derivative function, and the original function is right here. So if we wanted to evaluate this using the fundamental theorem of calculus, it would be f of 2 minus f of 1. And this problem should look familiar because we've actually done this problem before. Well, now plugging in, we have 2 ln 2 minus 2, that's f of 2, minus, putting in 1 into f of x, 1 ln 1 minus 1. And you guys are all good math students, and you know that ln 1 is 0. So, simplifying this, we can get that this equals 2 ln 2, and then minus 2 minus minus 1. So this becomes a plus 1. So minus 1. And that's an exact answer for our evaluation of this definite integral. Of course, it required us to be given this function. Right now, I don't expect you to be able to take the antiderivative of this and know that it's that. You'll get there, but not right now. So we're going to work on easier definite integral problems. But before we get to that, let's review some key integral rules. First of all, there's the constant multiple rule, which says that if you have some constant in an integral, that can just be moved out front. But it doesn't affect the integration. So the integral of c times f of x is the same thing as c times the integral of f of x. Another important rule is the sum and the difference, that if we're adding two functions in an integral, we can split up the integral and integrate them separately. But that only works with addition and subtraction. It doesn't work with multiplication and division. So this rule does not work. And some of you are going to try to do this, and it's gonna frustrate me or your whoever your teacher is. It does not work with multiplication or division, and that's because antiderivatives with multiplication and division require us to consider product rules and quotient rules. But we'll get to that later. So for now, we're just talking about addition and subtraction. And let's see this in action. Well, if we're integrating x dx from 1 to 3, we can geometrically evaluate this. So when x equals 1, this value is 1. When x equals 3, the y value is 3. So using the area of a trapezoid, which is just 1/2 our base times the sum of the two heights. And what the 1/2 does in front is it's averaging those heights. So we get 4. And over here, this is a constant times a function we already know. So this equals 2 times the integral from 1 to 3 x dx. And we've already found this to be 4. So this equals 2 times 4, which is 8. And over here, we did the algebraic or the geometric work to confirm that it's 8, finding the area of the trapezoid. So the key thing, the key idea is that if you're integrating a constant times a function, that the constant can be pulled out front. Write this down. Important. Seems obvious maybe, but as you start building more and more new ideas, it may seem less obvious. So make sure you understand it now. Okay, so finding antiderivatives. This is a skill we need to do. And we've already practiced this. So for example, if I have some function and its antiderivative, I sort of think of it like this. I mean, this is ignore me if you're confused. But imagine that there's a family, and this one set of the family, there's a woman and her name was Derivative, and and this woman Derivative had a brother, and the brother had a kid. Well, now she is anti-derivative. She's the anti-derivative. It's a joke. Okay, um, that's really funny stuff. I hope you understand the joke. It's pretty stupid actually. But anyway, let's say we have some function x. What would be the antiderivative? Well, using the power rule, this has to go up a power, and then we put a 1/2 in front to cancel off when the 2 drops down, so that we would end up with a 1. What about if I had sine? Well, what function has sine as a derivative? Well, we know that the derivative of cosine is negative sine. So if we do negative cos x, this would be the antiderivative. Because if you take the derivative of these functions, you'll get these ones back. Let's look at a couple more. E to the x. Oh, that's our favorite function. It's just e to the x. What about something like x cubed plus x minus 1? We'll treat each one of those independently. So x cubed becomes x to the 4th, and we put a 1/4 in front. And then x, we've already done that, 1/2 x squared. And minus 1 becomes minus x. And those are the antiderivatives. So now we're going to piece these together. So we're going to be given some definite integral, and we're going to find the antiderivative. And we're just going to we're saying that the inner function is the derivative. So the antiderivative is the original function. And once we find this function, then we can just evaluate. I know you're eager to see this in action. Here we go. So integrating this polynomial, we need to find the antiderivative. Well, the antiderivative of this is 2, the constant stays there, times 1/3x cubed. The 2 becomes a 3 because we're adding it, and then we put the 1/3 out in front. That's always how it is with the power rule. Plus, well, 3 is a constant, so 3 times 1/2x squared, and then plus 1 becomes plus x. And then what we're going to do, this is f of x. That is f of x. And what I want to evaluate, I want to find f of 3 minus f of 1. And the notation that we use, and this is new notation, we write after we find the antiderivative, we say that we're going to evaluate it from 1 to 3. So this bar means we're going to put in the 3 and then subtract and then put in the 1. So let's do it. So we get equals 2 times 1/3 3 cubed. I should always have parentheses. Plus 3 times 1/2 3 squared plus 3 minus, so I put 3 into everything, and then minus, new parentheses, putting in 1, 2 times 1/3 plus 3 times 1/2 plus 1. Well, this is quite a bit of fraction addition, but I'll do that quickly. I'll pause the video so you don't have to suffer with my slow math skills. All right, so this ends up being 31 1/3, and you should be able to do this math. That took me, about a minute or so of working, not super fast, but you need to be able to add fractions to be successful on the AP exam. So if that's something that's still vexing you, which it does for many, let's make sure that we have a good grasp of that. Okay, so I want to look at just a little bit more, but what I'm going to do is I'm going to stop the video here and start another video. So make sure to watch part 2 of this video system. Thank you very much. Goodbye.